Okay, so on Thursday, Mr. Deirdre played the lesson there for you on universal gravitation, okay, which had to do with this formula. We talked about it just briefly yesterday. Big G times M1 times M2 over R squared. And of course, we were using that as part of satellite motion yesterday. That is the force that provides the centripetal force that keeps any satellite in orbit. Okay, but from my understanding, it sounds like you guys didn't get to net gravitational force problems on Thursday. Okay, so what we want to look at here is net gravitational force problems. Now, it's just like what you would think, okay? It's net force. It's the vector sum of all forces. It's just the only force is gravity. Okay, so let's try a super simple situation here, okay, where we've got the Earth, okay, during a lunar eclipse. Okay, so during a lunar eclipse, the Earth moves between the sun and the moon. Okay, and then it casts a shadow on the moon. Sometimes you get a blood moon, okay, during that kind of thing. Okay, sometimes you can see the perfect curvature of the Earth passing over the moon. Okay, things like that. Okay, depending on where you are. So here's what we want to find out. We want to find the net gravitational force acting on the Earth in this orientation of the sun, the moon, and the Earth. Okay? How many directions is Earth being pulled in this particular situation? Two. It's being pulled towards the moon, and it's being pulled towards the sun. Okay. Now, from the formula, we know that mass obviously has a big role to play in the amount that something is attracted to something else. But we also know that how far apart they are plays a very big part in that as well. Agreed? Is the moon a lot closer to the Earth than the sun? Yeah. It takes 1 minute, okay, or sorry, 1 second for light to go to the moon and basically back. Okay, it's why there was virtually no interruptions in radio communication for the people when they landed on the moon. Okay, but it takes 8.3 minutes for light to get from the sun to the Earth. It's considerably further away, okay? Which means that R for the Earth to the sun is a much bigger number than R for the Earth to the moon. On the other side of that, the moon is going to be one of the masses in each one of these, or sorry, the Earth is going to be one of the masses in each of these calculations. But the difference between the mass of the sun and the mass of the moon is, well, gargantuan, okay? I mean, the sun is more massive than everything else in the entire solar system combined, and still by a significant margin. Okay, so let's see if we can do this. I want you to calculate for me right now, okay, using the numbers on your formula sheet. So that would be 3.85 times 10 to the 8 meters as the separation distance here. Okay, 1.50 times 10 to the 11 meters as the separation distance here, and then you've got your masses as well, okay, on your formula sheet. Mass of the Earth, 5.94 times 10, sorry, 5.98 times 10 to the 24. Okay, mass of the sun, 1.99 times 10 to the 30, okay, and the mass of the moon is 7.36 times 10 to the 22. Kilograms. Okay, so what I want you to do is calculate for me the net gravitational force acting on the Earth in this situation. Okay, I'll give you a couple minutes on that. All right, so we have two separate forces of gravity acting on the Earth. Okay, we have the force of gravity between the moon and the Earth. All right, so if we're going to calculate that, we're going to have to go big G times the mass of the Earth times the mass of the moon, okay, over the radius between the Earth and the moon squared. All right, so that's going to look like this. 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 times 7.36 times 10 to the 22, so mass of the Earth, mass of the moon, okay, divided by 3.85 times 10 to the 8, okay, and that number is squared. That's the most common mistake, is forgetting to square that in the calculation. Okay, so if I punch all that in, okay, 6.67 e negative 11, okay, 5.98 e 24, 7.36 e 22, divided by 3.85 e 8 squared. All right, so we're looking at 1.98 times 10 to the 20 newtons. Okay, that would be pulling the Earth this way on this paper to the left, but towards the moon, yes. Okay, then we've got the force of gravity between the sun and the Earth. That's going to be big G times the mass of the sun times the mass of the Earth over the average Earth-Sun distance, 1.5 times 10 to the 11 meters. Okay, so 6.67 times 10 to the minus 11 times 1.99 times 10 to the 30 times 5.98 times 10 to the 24 divided by 1.50 times 10 to the 11 squared. Okay, so that's going to be 3.53 times 10 to the 22 newtons. Okay, how do I find the net force? Vector sum of all forces. Okay, since the moon pulls the Earth away from the sun, and the sun obviously pulls the Earth towards the sun, that's simply going to mean subtracting those two numbers. Okay, so taking that number there, okay, and subtracting that number. Okay, so 3.51 times 10 to the 22 newtons towards the sun. How important is that? Pretty important, as net force is a vector quantity. You'd be surprised how often that gets forgotten on a question like that. Okay, is that a very hard calculation? Like a very hard question? You basically did the same calculation twice and then subtracted the answers. Okay, that's all a net gravitational force question asks you to do. Okay, now this one was pretty easy because they directly opposed each other. Okay, what if I threw an angle in there instead?
Draw a tail head.
Exactly, you just draw a tail to head like you would have in the first unit. So let's have you try this one. Okay, so now the moon's out over there. Okay, now I want you to calculate the net gravitational force on the Earth when the moon is 90 degrees offset to the right or to the left, depending on your point of view, okay, on that side there. Here's the good news. Do you get to still use those two big numbers you calculated in the last question? That's not going to change. The Earth and the moon are still the same distance apart. Earth and the sun are still the same distance apart. They have the same mass. So you get to use the 1.98 times 10 to the 20 and the 3.53 times 10 to the 22. You get to use those numbers over again, okay? But you have to realign them for a vector question now. Okay? Okay, so we already know what the values are, okay? And we know that one of them is way, way bigger than the other, okay? This is the force of gravity between the Earth and the sun, so FGSE, okay? And we know that it's 3.53 times 10 to the 22 newtons, right? The moon pulls the Earth that way, in this case up a little bit, okay? But that number is incredibly small. That's probably not even doing it justice. That's probably way bigger than it should be, okay? Like that. Okay? The Earth's, or the moon's effect on the Earth, okay, is, I mean, it's significant. We see it. We see the tides, all of that kind of stuff. But when it comes to Earth's orbit around the sun, not so much. Okay? And sure, it makes the Earth wobble a tiny bit, but not enough to really matter for us. Okay? That means that this is our F net. Okay, just makes a right angle triangle, so I just have to do Pythagorean theorem between the two numbers that I had. Okay, that'll give me that force there. Okay, sorry, this was 3.51, wasn't it? No. Gotta go back. Reusing the number. No, it was 3.53. Okay. So if I do that, okay, then I'm going to do my Pythagorean theorem here, and I'm going to get a number, okay, about 3.52 or so, okay, and then this angle here. Now, that's what their answer is. I think ours is actually going to be a little bit different because we used slightly different numbers to calculate this than they did. Okay, so let's get what our number is going to be. So we'll take our that, and we'll take our 3.52 there, okay, and then I'll square that. I need to put it in brackets. Okay, plus the moons, so another bracket, that was the 1.98, okay, and then square that. Okay, so I get 3.53. It barely changes the number, does it? It goes from 3.5277 to 3.5278. Doesn't really make much of a difference, does it? Okay, so that number is only negligibly bigger than the number we had already. Now we need to find the angle. Well, the Earth-Moon one is going to be the opposite side. The Earth-Sun one is going to be the adjacent side. If I go second tan, okay, of the moons, okay, divided by the sun, okay, I get 0.3 degrees, just like they did, okay? So it makes very little difference. We would never notice any change here living on planet Earth as the Earth goes around the sun and wobbles a little bit, okay? Like, when it comes right down to it, if this is the sun, okay, and the Earth is out here, the Earth's orbit does this. And it wobbles back and forth. All kinds of things pull on the Earth. Other planets pull on the Earth as it orbits the sun, okay? So its orbit is not a perfect circle, okay? It's pretty close, but it's not perfect. Okay, that okay with everybody? All right, so in this particular orientation, they are mentioning that this is the first quarter phase of the moon. So that means that this side of the moon here is in darkness. Okay, that side of the moon would be light, so we would see half the moon. That would be the first quarter. Okay, all right. Okay, now, did you guys work on these with Mr. Deirdre? The ones from the worksheet? Okay. There are a couple from the worksheet that I'm going to want you to do here, so let me bring it up. Okay, so I'll blow these up here, but I am going to want you guys to do let's say for sure 10 and 11, 9, 10, and 11. I'll just blow them up and we'll work on those. Okay, so trick to number 11 is that that's above the Earth's surface, right? So we have to add radius of the Earth to this number, right? Oh, sorry, that's number 10. Okay, so on this one here, we know the masses of each one. I think I have that here, hang on. Okay, so this one, so mass A is 10 kilograms, okay, B is 10 kilograms, okay, and C is 15 kilograms. Right? We are looking for the net gravitational force on B due to the other two. So this is just like the Earth, Sun, Moon question we did. Okay? I need to find the force of gravity between these two objects here. So that'll be 6.67 times 10 to the minus 11 times 10 times 10 divided by 0.5 squared. Okay, and then for this one here, 6.67 times 10 to the minus 11 times 10 times 15 divided by 0.5 squared. Okay, and then I just subtract those two numbers, and I've got my net gravitational force. Okay? All right, I would expect to see a question like that, like maybe, just objects like this, or maybe it's planets and moons or whatever on your unit exam as a gravitation question. Okay, because just giving you a, hey, plug the numbers into this formula question is not really going to test your understanding of it, but making you apply it to something like that does. Okay? All right, let's move on to gravitational field strength. This is the last thing, guys, in this unit. Okay, so universal gravitation deals with the force of gravity, that how hard two objects are pulled together. Okay, the force that's pulling them together. Field strength measures their acceleration towards each other. Okay, so while one is how hard they're pushed together, the other is how quickly they move towards each other. All right, are they going to be affected by the same things? Right? Are force and acceleration affected by the same things? Okay, then these two things are affected by the same things. Okay, they're affected by the mass of the object. Okay, they're affected by how far apart the objects are. Okay, all the same things. With field strength, okay, what we have to understand is the idea of a field. This is the first time that this is going to be covered in physics, okay, for you guys. And when you get to physics 30, you talk about electric fields, magnetic fields, gravitational fields. Again, lots of the forces that we deal with are field forces in physics 30. This is the only field force we deal with in physics 20. Everything else in physics 20 is a contact force. Tension, friction, okay, all of that kind of stuff, those all involve contact. They have to be touching each other. Okay? So gravity is a field force, which means that it can act over a sphere of influence, let's say. It doesn't have to be in physical contact with something else to pull on it. Okay? And we know that because obviously the Earth and the Moon are not in physical contact with each other, okay, but they are attracted to each other anyway. Okay? Everyone okay with that idea? So a field just means there's this area of influence, okay, around something with mass, okay, that will attract things to it. Okay? You have a gravitational field. It's pathetic, okay, but you have one, right? Because you have mass. And anything that has mass has a gravitational field. But you can't attract anything to you, okay, because the Earth's gravitational field is bigger than yours. Kind of. Lots bigger. Okay? Everyone okay with that idea? Okay, so both the Earth and the Moon obviously have mass, and as a result, they both have gravitational fields that surround them. Okay? We see evidence of the Earth's gravitational field on the Moon because it orbits the Earth. What evidence do we have of the Moon's gravitational field?
Tides.
Tides, exactly. Okay? Because we are inside the Moon's gravitational influence, we see that all the water on Earth is attracted to the Moon and generally flows that direction. Okay? All right, so these fields overlap. Which one is bigger? Yeah, the Earth's is bigger because the Earth is bigger. It is more massive, and thus it has a larger gravitational field. Now, weird thing about gravitational fields, they are always from the perspective of the bigger object. Okay? The smaller object is caught in the bigger object's field. And so when we're talking about the field strength, we're talking about the acceleration of the small one towards the big one, even though it's technically them towards each other. Okay? All right, so Michael Faraday was the scientist who came up with the idea of the field. Okay? He was dealing with magnetic fields and electrical fields, but he realized that some forces didn't actually require contact to work. Okay? If he would have done like with a bar magnet, and you put a bar magnet down, you put iron filings around it, they all kind of align towards it. They didn't have to be in contact with the magnet to be pulled towards it. Okay? So he had this idea that magnets have a field, electricity has a field, okay? Gravity also has a field. And that eliminated the need for all these magical invisible strings that connected everything, okay? That was kind of the previous explanation. Okay? All right, everybody with me so far? long as we understand what a field is, right? Area of influence or sphere of influence, okay, of an object's gravity. Okay, so if we just had the Earth, no moon, okay? We just had the Earth's gravitational field would look like this. All of the gravity would point towards the center of the Earth. And of course, the further away from the center of the Earth you get, the smaller that attraction would be. That's why the arrows get shorter, okay, as you move out. Everyone all right with that idea? Still pretty much the same as what we were talking about before. Okay, so that means that the further away I get, not only am I less attracted to it force-wise, but I will fall more slowly towards it. Okay? On the surface of the Earth, it's around 9.81 meters per second squared. Okay? But if I start moving away from the Earth, my acceleration due to gravity would also decrease, yes? Okay. It's acceleration due to gravity that is the measure of field strength. Okay? It's how quickly they move together. Right? So we often express field strength in one of two units. Newtons per kilogram. Okay? What are the base units for a Newton? Anyone remember?
Kilogram meters per second squared.
Okay, so a Newton is a kilogram meter per second squared. So newtons divided by kilograms just makes the kilograms go away, doesn't it? And what am I left with? Which are the units for acceleration, which is why acceleration due to gravity is the measure of gravitational field strength. Okay? You could write either one of these units and it would be right. Newtons per kilogram or meters per second squared, because they're the same thing. Okay, so here's where we arrive at our formula. Gravitational field strength is technically acceleration due to gravity. Okay? And so that means then that it's basically just manipulating this formula. Agreed? Okay, what's the other way to calculate this force that we just learned and we're literally just using?
The multiple masses one?
Right, the multiple masses one. Okay, so really what we've got here is like, can't write FG. Okay, m1 times m2, okay, over r squared with big G in there, okay, and then divide all that by m. Well, one of these is the smaller of the two masses, agreed? So is this. This is the smaller of the two masses. So if I put the smaller of the two masses in there, it cancels, and I'm left with that as my formula, which is on your formula sheet. Okay? The formula for gravitational field strength looks a lot like Newton's universal law of gravitation. Okay? It's just instead of solving for force in newtons, it solves for acceleration in newtons per kilogram or meters per second squared. Okay? So the mass that remains is always the one generating the field, so the bigger one. Okay, so if we're talking about something caught in the Earth's gravitational field, we don't use the mass of the object that's caught, we use the mass of the object that's generating the field. That would be Earth. Okay? All right, everybody okay with how that formula comes about? Okay, basically we're just saying this, right? Force of gravity equals force of gravity. M times G equals big G times M1 times M2 over R squared, and then one of the M's cancels, and that's how I get that formula. Okay? Okay, now, the Earth's gravitational field is obviously not as simple as what we saw on the previous screen, because there's this other thing in our neighborhood called the moon. Okay, and the moon has its own gravitational field. Well, fields work just like forces. Okay? Net gravitational field strength is the vector sum of the field strengths that make it up. Okay, so it would be put them tail to head and all that kind of stuff. So on the far side of the Earth, where the moon isn't located, the field looks pretty normal. But on the side where the moon is, okay, we can see that the arrows kind of get messed up. Okay, and in fact, is there a point where there would be no net gravitational field? Yeah. Okay, right here. There's actually a whole bunch of spots like this around the Earth. They're called Lagrange points. Okay, and they're points of net zero gravity based on the sun, and the moon, and the Earth, and even other planets and things like that. Okay? Now, if you're a rocket scientist and you're trying to send something to the moon, is this something you need to be concerned about? Definitely. You do not want the engines firing towards the moon the whole way there, do you? A, that would use a lot of fuel, and B, there comes a point where gravity is also pulling you towards the moon. Like you've got, yes, you're escaping Earth's gravity for a long, long way, but there is a tipping point that's obviously much closer to the moon than the Earth, where that's going to flip. And now the moon's gravity is accelerating you towards the moon. And you have to flip the ship around and start firing the engines toward the moon in order to slow down. Okay? These are all things that people who do rocket science have to think about when they're trying to put a probe in orbit around another planet or land a probe on another planet or things like that. These are all the field strength is stuff they've got to consider. Okay? And sometimes the gravitational field itself isn't perfect. Okay? This assumes that Earth's mass is all distributed evenly. Is it? Not at all. Okay? Earth's mass is not distributed evenly. We've got continents that represent more mass. They're sitting in certain places. Okay? So the Earth's mass is not perfectly distributed, and that affects its field shape. Nothing we're ever going to deal with, just something we need to understand. Okay. We already talked about that. Okay. Not the one I'm on. Okay, let's have you guys try 1 and 2. I'll make them a little bit bigger here so you can read them. But these. So for number 1, okay, the first one is if it's saying it's 3 Earth radii from the Earth's surface, how many is it from its center? 4. Right? If it's 3 from the surface, add 1 more to get to the center. You got 4r from the center. Okay, for part B, what's the magnitude of the gravitational acceleration of this satellite? Well, gravitational acceleration is gravitational field strength. So we would have big G times the mass of the Earth over r squared. R is going to be 4 times the Earth's radius. Okay, so we'll have 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24, because it's the Earth's gravitational field. Okay, and then we would go 4 times 6.37 times 10 to the 6, okay, squared for our radius there. Okay, so if we punch that in, we should get the 6.11 times 10 to the minus 1, but we'll double check here. First we'll do this. Okay, so there's our radius that we're going to use. Okay, and then on the top we got 6.67, second E negative 11, 5.98 E 24, close the top, okay, and then divide by the bottom, which is that number there, squared. Okay, I think that's what they got, right? Yep. Close. I mean, they get 0.611, we get 0.614. Why? Because I use the numbers from our sheet. The numbers from this book are slightly different. Okay, they use 5.97 for the mass of the Earth instead of 5.98, and they use 6.38 instead of 6.37 for the radius of the Earth, so their numbers are a little different. Okay, all right, how are we doing on number 2? How many people have done 2? Okay, do we need to go over number 2? Yes? No? Yes? Okay. All right, so we have an 80 kilogram astronaut that's in orbit, 3.20 times 10 to the 4 kilometers from the Earth's center. Okay, so they gave us the radius, but they gave it in kilometers, so that's just going to be 3.2 times 10 to the 7 meters, okay, to get it into meters. And then we have an 80 kilogram astronaut, so that's the mass of the astronaut. Not that that's going to matter. Okay. Calculate the magnitude of the gravitational field strength at that location. So that goes back to this. Big G times the mass of the Earth over r squared. Okay. Still 6.67 times 10 to the minus 11. 5.98 times 10 to the 24 because it's the Earth. okay, and then we divide that by 3.2 times 10 to the 7 squared. Okay, mass of the astronaut is irrelevant. All things fall at the same rate. Gravitational field strength is acceleration due to gravity. So mass of the astronaut doesn't matter. It could have been a 600 kilogram mass. It could have been a 15,000 kilogram dump truck. It could have been anything. The answer would end up the same because all things fall at the same rate. Okay, so we should get 3.89 times 10 to the minus 1 newtons per kilogram. Okay, but we'll just punch it in just to make sure here. I'm just going to cheat a little bit here. Yep, 0.389, so we're good. Okay, everyone all right with that? Okay, and then what would the magnitude of the gravitational field strength be if the astronaut was orbiting the moon with the same separation distance? Okay, what's the only thing I need to change in here?
Radius.
Nope, because it actually said at the same distance. So I get to keep the radius.
Moon's mass.
So just put the moon's mass in. Okay, so I go back to here where I had 5.98 times 10 to the 24, and I put in 7.36 times 10 to the 22. Okay, much smaller obviously because the moon has less mass and would have less gravitational field strength. Okay, everyone good with that? Okay, try number 3. Is number 3 asking for acceleration due to gravity or force of gravity? Force of gravity. Okay, whole reason that I put this one on there is to make sure that you're reading the question carefully. This is the most common mistake when it comes to gravitational field strength versus force of gravity questions. Okay, a gravitational field strength question will either use those 3 words, gravitational field strength, or it'll use acceleration due to gravity, whereas a force of gravity question will say gravitational force. Okay, so this is actually one of these questions where the 70 kilograms now does matter. Okay, so we would have the 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 times 70 divided by 6.6 times 6.37 times 10 to the 6 squared. Okay, so if we do that, okay, so we should get about 15 or 16 newtons. Okay, 2 significant digits would say 16 newtons. Okay, for our answer there. Okay, so the lesson to get out of that one, read the question carefully. Make sure that you're giving it what it asks for. Okay, gravitational field strength and gravitational force questions will often give you exactly the same information. Sometimes you'll need it all and sometimes you won't. Okay, the first question we didn't need the mass of the astronaut. This question, we did. Okay, questions on that? Okay. So, here's our plan going forward. Okay, tomorrow we're going to do unit exam review, because obviously I have a unit exam on Thursday. Okay, I'm going to give you the gravitation assignment now, and then whatever time we have on Friday after we go over the test, you will also have to work on that. Okay, it's going to be a lot like this one. It's not going to take you very long, and it's fairly straightforward. You guys slaughtered this one, so I assume you will do the same to the gravitation assignment, and I want you to have the opportunity to put that in your marks and bring your mark up a little bit more. Okay, so I'm going to give you that now, and you can get started on it. It's all the stuff we've gone over since Thursday. So universal gravitation, satellite motion, and gravitational field strength. Okay? Okay guys, so just want to kind of quickly go through that assignment there just so you kind of know what we're looking for. Make sure you look at the point values. They're a pretty good indication of how much work you need to do or how little work you need to do in some cases. Okay, so for number one, you're told how far Jupiter is from the sun. You're told Jupiter's mass. You're just looking for the force of gravity between the two. Okay, really don't overthink that one. Okay, in number two, you're given the orbital period of Uranus, but it's in years. Okay, so you'll probably have to do a little conversion of that. A little note here. How many days in a year? 365.25. Why do we have a leap year every 4 years? Okay, we have a leap year every 4 years because it actually takes 365 1/4 days to orbit the sun. So when you're factoring that in, make sure you factor that in, okay? Because it does make a difference when you're talking about 84 quarters of a day, okay? All right. So in that one there, you're just looking for the orbital radius of Uranus. I would say since you have the mass of Uranus and the sun, that shouldn't be too hard. Okay, for number three, similar idea, but it gives you the period of orbit in days. Okay, and then it gives you the distance. You're looking for orbital speed there. Okay, so a little bit of manipulation on that one. Interesting bit of trivia. 1 year on Venus is less than 1 day on Venus. A day on Venus is actually 228 Earth days. It actually rotates that slowly. Okay, number four, Cavendish and a Cavendish apparatus. So we didn't talk about this very much, but a Cavendish apparatus is what we call a torsion balance. So there's two really big masses and two really small masses, and gravity pulls them towards each other. Okay, so you're just looking for the force of gravity here using that formula. Okay, you know their masses, you know how far apart they are. Don't overthink it. Okay, for number five, you're given the force of gravity between two electrons. It's obviously an incredibly small number because electrons are very, 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 very small. And electrons are also identical. So that might be useful when you're trying to find the mass of an electron. If we are talking about the gravitational force between them, all electrons are identical. Okay? In other words, they have the same mass. Okay, for number six, Mimas is a moon of Saturn. I think it's the one that looks like the Death Star. Okay, it's got like a big crater in it that makes it look like the Death Star. Okay, it has an orbital radius there that you are given and an orbital period that you are given, but in hours. Remember, everything we do requires orbital period to be in seconds. Okay, you're looking for the mass of Saturn from that. Number seven is talking about Apollo 2, okay, orbiting the moon. You're given things in kilometers. Remember that we need them in meters, okay? And that first number, the 111 kilometers, that is from the surface, okay? Which it becomes obvious when they tell you the radius of the moon is 1,785 kilometers. You can't orbit inside the moon, okay? So that is above the moon's surface. Okay. And for number 8, spy satellite. Sometimes people get confused on this one. We only spy on ourselves. Okay, so this spy satellite is orbiting Earth. It doesn't explicitly say that, but I'm going to explicitly say that this spy satellite is orbiting Earth. Okay, because that's sometimes a useful piece of information. Okay, number 9 is talking about Mars's natural satellites, its moons. Okay, just simple satellite motion calculations there. Number 10 is like the ones we did today, the net gravitational force questions. Okay, we are looking for the net gravitational force on mass 1. That is the top right. okay, it is being pulled that way, and diagonally, okay? One thing to keep in mind, the dimensions of this square are 1 meter by 1 meter. The distance across is not 1 meter. Most common mistake on that one, okay? From this corner to this corner here, okay, is more than 1 meter. Okay, I'm just putting that out there because sometimes people make that mistake. Okay, and then for number 11, okay, just another satellite question, period around the sun. Okay, number 12, acceleration due to gravity, so field strength question like what we were talking about today. Okay, and number 13 is another just universal gravitation question. Okay, so there's only like 2 questions on here that are any significant amount of work. Okay, the rest are all pretty straightforward. All right, have at her.